Today I'd like to speak about the engineer Alfred Landon Reeves and the design and construction of the longest single-span masonry arch in the United States. It is the Cabin John Bridge, also known as the Union Arch, of the Washington, D.C. Aqueduct, designed and built from 1856 to 1864. This study was completed with my colleague David Simmons of the Ohio History Connection. At mid-19th century, the city of Washington, with a population of about 50,000, had no central water supply. Individuals collected water from small local streams or springs or from private wells. This was unacceptable for the capital of an aspiring United States. Therefore, in 1850, the U.S. Congress commissioned a study to determine upon the best and most available mode of supplying the city of Washington with pure water. It was common at this time for Congress to assign such infrastructure studies to the U.S. Army Corps of Engineers. Accordingly, Lieutenant Colonel George W. Hughes was charged with the study, and a report was completed in January 1851. The only water source evaluated in detail was that from a stream within Washington called Rock Creek, because the appropriations were not sufficient to study alternate water resources, especially the Potomac River. This study, completed in only a few months, relied on work completed by non-military or civilian or civil engineers. In the report, Colonel Hughes stated that from the exigency of the service, it became necessary to employ a civil assistant, and we have availed ourselves of the surveys of the Chesapeake and Ohio Canal, which was a canal along the Potomac previously completed by civil engineers. And I will take this opportunity of saying that for many practical details of this report, I have availed myself freely of the admirable report of Messrs. Jarvis and McAlpine, both gentlemen of enlarged experience in hydraulics, to whom my acknowledgments are due. John B. Jarvis and William J. McAlpine were prominent civil engineers who had worked on the water supply for Albany, New York. The report clearly suggested that an additional study that considered the Potomac River as a water source was needed. Therefore, Congress and the President in September 1852 requested another study for determining the best manner of affording to the cities of Washington and Georgetown an unfailing and abundant supply of good and wholesome water. This study was again entrusted to the Corps of Engineers of the U.S. Army, who assigned it to Lieutenant Montgomery C. Meigs. A report was completed in February 1853. The report strongly recommended the Potomac River at Great Falls as the water source. This is a drawing of the Washington area from the Washington Aqueduct Office. The original plan consisted of a dam on the Potomac at Great Falls and an aqueduct along the Potomac, shown in red, about 13 miles long, from Great Falls to two Georgetown reservoirs, about 145 feet above high tide in Washington. The report repeatedly emphasized that with such a reservoir elevation, water could be supplied without pumping to an elevation 14 feet above the upper floor of the Capitol, a point not lost on Congress. The proposed aqueduct had to cross several small streams, gullies, and ravines, but by far the largest was that of Cabin John Creek. For that crossing, with a principal objective of advancing an economic and easily constructed aqueduct, Meigs proposed a conventional viaduct of masonry arches, which he described as follows. The Cabin John Bridge proposed will be 482 feet in extreme length, its greatest height 101 feet, width 20 feet, and it will consist of 6 semicircular arches of 60 feet span, resting upon piers 7 feet thick and 20 feet long at the top, and of various heights, the highest being 52.5 feet. In the report, Meigs acknowledged the contributions of civilian engineers. I have used with confidence the formulas d'Aubusson as reduced to English units in his admirable work on hydraulics, so well translated by Mr. Joseph Bennett, civil engineer, of whose assistance I have had the advantage of conducting the Rock Creek survey. To Mr. William H. Bryan, civil engineer, who conducted all the explorations for bringing the water from the Potomac, I'm under particular obligation. His knowledge of the river, gained during a long experience upon the Chesapeake and Ohio Canal, was invaluable. It enabled him to make valuable suggestions, many of which I have adopted, and indeed, we have discussed together the various means of mastering the difficulties of the problem, till it would be difficult to determine with which of us many of its features originated. So by Meigs's own words, the original aqueduct plan was genuinely a collaborative work between him and the civil engineer William H. Bryan. Montgomery Meigs grew up in Philadelphia, Pennsylvania. His father was a physician, a graduate of the University of Pennsylvania, who upon graduation moved his family to Augusta, Georgia, where Montgomery was born in 1816. However, soon after, the family moved back to Philadelphia. Meigs graduated from West Point in 1836, fifth in his class, and became a member of the elite Corps of Engineers. In 1850, Meigs became assistant to General Joseph G. Totten, chief engineer of the U.S. Army. The 1853 report was pivotal to Meigs's rise in prominence. Immediately following the report, Meigs was promoted to captain and appointed chief engineer of the then-approved Washington Aqueduct and the U.S. Capitol extension. Moreover, in February 1855, Meigs was also made chief engineer of the new General Post Office, then under construction in Washington. These responsibilities evidently required many additional engineers. This is an image of Meigs seated, surrounded by 5 of his principal assistant engineers. From left they are Alfred L. Reeves, Edmund D. Myers, Charles G. Talcott, and William R. Hutton. Reeves and Hutton were to work closely together on the Washington Aqueduct and specifically on the Cabin John Bridge. Reeves' academic training for advanced civil engineering work was unique for an American. He was born in Paris, France in 1830 because his father, William Cabell Reeves, was the American minister to France under President Andrew Jackson. He was raised on a family estate in Virginia called Castle Hill, approximately 12 miles from the home of President James Madison. He graduated from Virginia Military Institute in 1848, first in his class in engineering studies. His father was again appointed minister to France in 1849, and Alfred joined his family there with the ambition of enrolling in arguably the top civil engineering school in the world at that time, the École des Ponts et Chaussées. After a year of preparatory studies, he passed a rigorous entrance examination and became the first American admitted to the prestigious school. He graduated in December 1854. In his own words, he ranked among the first in his class. In recognition of his academic achievements, the French Minister of Public Works approved a gift to Reeves of some 150 volumes of technical works, including the complete set of 70 volumes of the Annals of the École des Ponts et Chaussées. This was very likely the most important collection of civil engineering technical and practical knowledge in existence, which Reeves later generously shared and kept at the Washington Aqueduct Engineering Office. There are collections of Reeves' papers at the National Archives, at Duke University, and at the University of Virginia. The University of Virginia collection includes some of Reeves' notebooks and coursework. Of interest in context of the Cabin John Bridge is his paper, written in French, entitled Competition for a Large Bridge. In this paper, Reeves discussed the longest single-span masonry arch then in existence, the Grosvenor Bridge over the River Dee in Chester, England, designed by George Rennie and completed in 1834 with a span of 200 feet. Reeves used several features of Rennie's design for the Cabin John Bridge. The variation in the sizes of the arch stones, or voussoirs, from the top of the arch to the supports is almost the same for both bridges. Both designs have a backing arch, shown highlighted on the slide. Both do not use an earth fill, and both have full walls between the arch and the top surface. In the same paper, Reeves also described the theory of Mr. Méry. Méry published a paper in the Annals of Ponts et Chaussées in 1840 in which he devised a graphical structural analysis method for predicting the axial forces in an arch and stated criteria that, if met, assured that an arch could safely carry the imposed loads. Therefore, Reeves knew both the most advanced British masonry arch designs and the most advanced French graphical analysis techniques. Reeves returned to the United States in January 1855, and after a brief employment with the Virginia Midland Railway, Reeves was hired as an assistant engineer in May 1855 with initial responsibilities primarily on the U.S. Capitol extension and on the General Post Office building. One of his many tasks was to make all necessary arrangements for putting up the heavy scaffolding to be used in pulling down the old and putting in the new dome. Reeves' sketch, shown on the left, indicates that he devised an iron wire and pulley system powered by an exterior steam engine, technologies that he later applied at the Cabin John Bridge. Incidentally, the iron wire ropes were supplied by John A. Roebling Sons Company of Trenton, New Jersey. In June 1855, Reeves accompanied Meigs along the C&O Canal to the Great Falls and beyond to the Seneca Creek quarries. In mid-November 1855, Reeves was named division engineer at Great Falls to temporarily replace an engineer who had become ill. With Reeves at the engineering department office at Great Falls, Meigs and Reeves began considering alternate detail designs for crossing the Cabin John Creek. The original 1853 proposal to build a 6-span masonry viaduct was not developed further. Rather, Reeves designed and estimated the cost of a 5-span viaduct as shown on the drawing. Although it can't be read at the resolution of the slide, the highlighted area on the left has a pencil statement which says, "Drawing by Mr. Reeves destroyed by fire." So this extant drawing at the Washington Aqueduct office is a replicate drawn very likely by his colleague, William R. Hutton. The journals of Montgomery Meigs hint at the interactions between Meigs and Reeves. His entries include the following. January 9, 1856, I saw at the engineering department in the Annals of Ponts et Chaussées. It was extraordinary for a field engineering office to have these volumes. They were clearly the volumes gifted to Reeves for his academic achievements at Ponts et Chaussées. January 16, 1856. Today I spent some time with Mr. Reeves in looking over his drawing of the Cabin John Bridge Arch, the 5-span design, investigated by Méry's geometrical construction. It was Reeves who analyzed the arches using Méry's method, which he learned at Ponts et Chaussées. February 6, 1856. I looked over some papers upon bridges today at the department and wrote to Professor Mahan at West Point to ask him where he found the detailed description of the Dee or Grosvenor Bridge over the Dee at Chester, England. This is the greatest span now standing in stone. It is 200 feet. I should very much like to build such a one. These facts about the Grosvenor Bridge were known to Reeves since his studies at Ponts et Chaussées. February 9, 1856. Today I went to the patent office to look up what is in its library upon the subject of bridges. I found a description of the great Dee Bridge at Chester called the Grosvenor Bridge of 200-foot span. The patent office apparently held volume 1 of the transaction of the Institution of Civil Engineers, which described the Grosvenor Bridge on pages 207 to 214. Reeves must have completed Méry's graphical analysis for an arch with a single span of 200 feet in January or February 1856 to show the feasibility of such a design, so that it is likely that a decision was made to proceed with the design of a single arch with a 220-foot span by the end of March 1856. William R. Hutton, who was also at Great Falls in 1856, noted that the present single span of 220 feet was suggested by Mr. Alfred L. Reeves, then employed as an assistant engineer to Captain Meigs, and then it was taken up by Captain Meigs. Although the decision was made to proceed with the 220-foot span arch, Congress did not allocate funds to continue with the design and construction of the aqueduct. Therefore, work was suspended in July of 1856. While it did not fund the aqueduct work, Congress requested a study for new bridges over the Potomac at Washington. With a strong recommendation from Meigs, the 26-year-old Reeves was appointed engineer in charge of the study on September 13, 1856. Reeves completed his study of Potomac River bridges and submitted his report on February 5, 1857. In 5 months, Reeves completed a hydrographic survey. He suggested navigation improvements and presented 4 bridge designs: a conceptual design for replacement of the existing Long Bridge, a new bridge using the Potomac Aqueduct piers, and 2 alternate suspension bridge designs at the location of rock outcroppings called the Three Sisters in the Potomac. Reeves' drawings, which are part of his report, exist in the National Archives. The top drawing is a partial elevation of Reeves' design for the replacement of the Long Bridge. It consists of sets of stone arches with spans of 120 feet, a viaduct of brick arches of 20-foot span, and 2 draw spans. Reeves also submitted the drawing below that shows a cast iron arches with spans of 200 to 250 feet, but he did not develop this design in detail. Reeves suggested repurposing the piers of the existing Potomac Aqueduct by replacing the existing aqueduct structure with stone arches and extending the piers vertically to support 8-foot deep iron plate girders to accommodate both a railway and a road above. He cited the bridge of Bercy in Paris as a successful example of a bridge design that accommodated multiple modes of transportation. Reeves further submitted 2 designs for suspension bridge at the Three Sisters in the Potomac. One design used a single span that Reeves said was a slight modification of Charles Ellet's suspension bridge over the Ohio River at Wheeling, which, incidentally, had been severely damaged in a windstorm in May 1854. Reeves also proposed a second design. This was a 2-span bridge intended to carry a railroad as well as a common road. Perhaps to show his familiarity with current suspension bridge design, Reeves stated that his proposal was similar to John Roby's famous railroad suspension bridge over the Niagara Gorge, completed in 1855. Reeves presented considerable detail for these suspension bridge designs. These are drawings of the towers for the proposed 2-span design. They really show that Reeves was talented in architectural detailing and design. Alfred Reeves submitted his report in February 1857. Congress appropriated $1 million for the Washington Aqueduct, and work on it was resumed. On March 14, 1857, Meigs created a new division of the Washington Aqueduct, less than 0.6 miles long, centered on the Cabin John Bridge, and named the 27-year-old Reeves division engineer in charge of construction of the bridge. A fire at the Cabin John Engineering Office on November 18, 1856, destroyed Reeves's drawings and computations for the 220-foot single-span arch. But by April 21, 1857, Reeves had reanalyzed the arch using Marie's method and completed the detailed design of the bridge and the centering. This is an example of Marie's graphical analysis of the arch. It's obviously not possible to explain the meaning of the many lines in a short time, but the analysis fundamentally showed that a line of thrust that satisfied equilibrium fell within the arch voussoirs along the entire span, and therefore that the arch was able to carry the imposed loads. This drawing is not the analysis done by Reeves in 1857, but rather one done by him much later in July 1859, when work on the aqueduct had again stopped because of a lack of funds. This 1859 work must have been done for presentation to create a formal engineering record. Some geometric features of the final design are as follows. The arch axis was a 110-degree circular arc with a radius of curvature of 134 feet. The span was 220 feet, and the arch was 20 feet, 4 inches wide. On the right-hand side, you'll see that there was an 8-foot diameter masonry aqueduct conduit on top of the arch. It had foundations made of natural hydraulic cement concrete. 9 voussoir sizes were used, with thicknesses varying from 4 feet 2 inches at the crest to 6 feet 2 inches at the supports or spring points, almost the same as those of the Grosvenor Bridge. It had a stepped backing arch like the Grosvenor Bridge. There were solid spandrel walls, but behind them there are arch structures, not an earth fill. This and other drawings are archived at the Washington Aqueduct Office. This drawing has an important note, not visible at this scale, that states no joint to be more than 1/8 of an inch. This is an extremely tight tolerance on joint size. It was achieved by using an abrasive medium and rubbing the stones with a flat iron plate. But before any voussoirs could be placed, a critical work had to be designed and constructed: the wooden centering or false work for the arch. This is a drawing of Reeves's wood centering and system for lifting the stones using an exterior frame, Roebling wire ropes, pulleys, and a steam engine. 4 or 5 voussoirs formed the 20-foot width of the arch. Therefore, the centering consisted of 4 parallel frames, each with the fan timbers to form circular arcs. Incidentally, in another drawing that you see on the lower right-hand side, Reeves drew a caricature of himself smoking a cigar and paddling in the backwater. A critical aspect of false work are provisions that allow for adjustments as the center deformed under the weight of the stones, provisions that also facilitate removing or striking the centering when an arch is complete. Reeves' decentering details consisted of 4 pairs of wedges, 1 pair over each frame at every voussoir location. The system was essentially the same as that used for the Grosvenor Bridge. In a July 1857 letter to his brother, Reeves proudly stated that the center for my great arch is finished. This is an image of the completed centering, very likely taken in the late fall of 1857. But much more work had to be done before placement of the voussoirs could begin. Meigs and Reeves had decided to use granite from Quincy, near Boston, Massachusetts, about 750 miles away by boat for the voussoirs of the arch. Quincy granite had been successfully used for waterworks and harbor works in Boston, and the Cabin John contractor was experienced in working with the stone. Therefore, quarried granite was shipped by sea from Boston to the port of Alexandria, Virginia. From there, it was barged on the Alexandria Canal, shown in red. It was then barged across the Potomac Aqueduct and then up the Chesapeake and Ohio Canal to Cabin John Creek. By the middle of October 1857, Reeves had dammed Cabin John Creek and constructed a locked lateral canal from the Chesapeake and Ohio Canal to the bridge site. After the stones were sized and polished, they were lifted by the steam hoists and transferred to rolling cars with manual winches for distribution along the length of the bridge. Incidentally, the right-hand side of this drawing has very light shadows that denote the interior arch structures behind the spandrel wall. During the summer of 1858, Reeves oversaw the placement of nearly 600 large granite voussoirs. And the final voussoir was placed on December 4, 1858, and as Reeves noted, at 2 p.m. Although keyed, the Aqueduct Bridge was far from complete and continued to be subject to congressional funding vagaries. In July 1859, Reeves and every engineer employed on the aqueduct were laid off for want of the necessary funds. Reeves stated that, at the same time, but unofficially, I received from Captain Meigs a letter requesting me to remain connected with the work. On July 17, 1860, Meigs himself was replaced as chief engineer of the Washington Aqueduct, perversely because of his scrupulously honest management of congressional funds clashed with Secretary of War John Floyd's patronage practices. On Floyd's removal, Meigs was reinstated as the chief engineer on February 21, 1861. These disruptions inevitably delayed progress on the bridge. This was the condition of the Cabin John Bridge on February 22, 1861. The backing arch had been completed and the interior arch structures were being constructed. But Meigs and Reeves had only a few weeks of professional and personal rapport left. On March 9, 1861, Meigs demanded an oath of allegiance to the Union from every engineer, and Reeves signed the oath. On March 18, 1861, Meigs ordered the sculpting of the following inscription on the Cabin John Bridge: Union Bridge, Chief Engineer Montgomery C. Meigs, U.S. Corps of Engineers. Assistant Engineer Alfred L. Reeves, Civil Engineer. Fort Sumter was attacked on April 12, 1861, and Virginia seceded from the Union on April 17, 1861. Reeves resigned from the Washington Aqueduct and later joined the Engineer Bureau of the Confederate States. Meigs deleted Reeves' name from the inscription and substituted Esto Perpetua. Meigs was soon promoted to Brigadier General and appointed Quartermaster General of the Union Army. He served with great distinction until 1882. Reeves rose to the rank of colonel in the Confederate Army and effectively headed the Engineer Bureau of the Confederate States. Meigs and Reeves never reconciled after the Civil War, and Reeves never again worked in Washington. In June 18, 1862, Congress transferred jurisdiction of the Washington Aqueduct to the Department of the Interior. William R. Hutton, Reeves' colleague, was chief engineer during 1862-1863, and Silas Seymour served from 1863 to 1864. The Cabin John Bridge was completed under their leadership. After 2 trial water flows and repair of some leaks, the Washington Aqueduct and the Cabin John Bridge were placed in service on July 29, 1864. The performance of the Cabin John Bridge over time has been exceptional. The conduit served continuously from 1864 to 1891. The only alteration made was to convert the top surface to a roadway. In 1911-1912, approximately 500 feet of cast iron lining was installed in the aqueduct conduit to stop leaks. The space between the cast iron lining and the original brick conduit was filled with Portland cement grout. Because of increased water demand, a second parallel conduit seen below the arch in this slide, or an inverted siphon, was built between 1922 and 1928. There have been no observable support settlements nor deterioration of the granite voussoirs. But there has been deterioration of the sandstone spandrel walls and parapets. The sandstone parapets were repaired in the 1970s. Salting of the roadway ended in the 1980s. A 3-ton load limit was imposed, as well as a 15-mile-an-hour speed limit. Alternate stone conservation practices, such as blast cleaning, coatings, and consolidants, were carefully evaluated in the 1990s. Selected deteriorated spandrel stones are being continuously replaced currently. The Cabin John Bridge forms a 1-lane section of MacArthur Boulevard in Washington. The Cabin John Bridge, designed and built by Alfred L. Reeves, civil engineer, is still today the longest single-span masonry arch in the U.S. As part of the Washington Aqueduct, it has provided water for both Washington and Georgetown for close to 160 years. Thank you.